The basic nature of oxides increases from magnesium to barium. With the exception of beryllium oxide, the group 2 metal oxides are basic anhydrides. This means that they react with water to form metal hydroxides. All the group 2 metals can react with halogens, forming halide compounds. These reactions usually occur at high temperatures. For example, calcium fluoride forms when calcium metal reacts with fluorine gas. A sample of fluorite, a naturally occurring mineral of calcium fluoride, is shown in the photograph. The best synthetic route for preparing beryllium fluoride is to heat ammonium beryllium fluoride until it decomposes, as shown in the equation here. Beryllium chloride can be formed by reacting beryllium oxide with chlorine gas in the presence of carbon. Carbon monoxide is a byproduct of this reaction. The halide salts of the alkaline earth metals are essentially ionic in character, with the exception of the halides of beryllium. The beryllium halides are primarily covalent and thus are soluble in organic solvents. In the solid state, beryllium chloride has a chain structure. However, in the vapor phase, beryllium chloride forms a dimmer. These dimmers dissociate into monomers at very high temperatures. The halides of the group 2 elements are often found as hydrates. But these salts are complexed with fewer water molecules down the column. Thus, magnesium chloride is an octahydrate, whereas barium chloride is found as a dihydrate salt. These salts can be dehydrated upon heating, leaving anhydrous salts. It should be noted that beryllium and magnesium salts will undergo hydrolysis upon heating, though, in general, the fluorides tend to be less soluble than the chlorides, because of the higher lattice energies associated with the fluoride salts. All of the group 2 metals, with the exception of beryllium, react with hydrogen to form metal hydrides. The reaction involving the formation of calcium hydride is given here. Beryllium hydride can be produced by reacting beryllium chloride with lithium aluminium hydride. The group 2 metals react with acids in a single replacement reaction, releasing hydrogen gas as a product. As a family, the alkaline earth metals have large negative reduction potentials. This feature reflects the strong tendency of the metals to lose electrons, otherwise known as oxidation. Since oxidation cannot occur without reduction, they can be considered good reducing agents. Beryllium has a lower reduction potential than the other group 2 metals, because its cation is smaller and has a larger atomization energy. In liquid ammonia, the group 2 metals dissolve to form solutions with a deep blue-black color. Ammoniate salts of the general formula shown here can be recovered from these solutions. The carbonates of the group 2 metals are insoluble. They can be prepared by reacting soluble carbonate salts, such as group 1 or ammonium carbonates, with soluble salts of the group 2 metals. One such reaction is shown here. A photograph of the mineral calcite, a naturally occurring form of calcium carbonate, is shown here. The group 2 metal carbonates decompose upon heating to form the oxide and carbon dioxide, as shown for calcium carbonate here. The White Cliffs of Dover consist primarily of calcium carbonate. The thermal stability of calcium carbonate increases as the metal cation increases in size. Beryllium carbonate is unstable and must be kept in a carbon dioxide atmosphere. The sulfate salts of the group 2 metals are white solids that are heat stable. Beryllium sulfate and magnesium sulfate are water soluble. But the solubility of this class of compounds decreases down the column. This is because beryllium and magnesium ions have higher hydration enthalpies than the other metals in the group. The group 2 metal nitrates can be prepared by dissolving the carbonates in dilute nitric acid. This class of compounds repeats the pattern of the decreasing tendency to form hydrates down the column. For example, magnesium nitrate is found as a hexahydrate, but barium nitrate is anhydrous. When heated, all the group 2 metal nitrates decompose to form oxides, as shown in the equation for the decomposition of calcium nitrate. The alkali earth metals are used for a variety of purposes. We'll wrap up this module with an overview of the uses of these metals. Beryllium is used in many industries. It is used to prepare several alloys. The copper beryllium alloy is used to manufacture high-strength springs. Metallic beryllium is used for the windows of X-ray tubes. The inhalation of beryllium dust, vapor, or its compounds can cause berylliosis, a serious form of mental poisoning. Magnesium is also used to prepare alloys. A magnesium-aluminium alloy is used in the construction of airplanes. Magnesium metal is used in flash powders and flash bulbs for cameras. Milk of magnesia, a suspension of magnesium hydroxide, is used as an antacid. Magnesium carbonate is used as an ingredient in toothpaste. Calcium is used in the extraction of metals from oxides, when they are too difficult to reduce with carbon. Calcium, along with barium, has been used to remove air from vacuum tubes. The radioactive salts of radium are used in the treatment of cancer. In certain respects, beryllium does not behave like the other group 2 metals. In particular, the compounds of beryllium have a significant degree of covalent character and are easily hydrolyzed. This is due to the exceptionally small atomic and ionic radii observed for beryllium, as well as its high ionization energy and electronegativity compared to the other group 2 metals. Beryllium can achieve a maximum coordination number of 4. This is because there are a maximum of 4 orbitals in beryllium's outermost energy level, namely the 2s and 2p orbitals. The other group 2 metals can utilize the d orbitals to have a coordination number of 6. Beryllium oxide and beryllium hydroxide are amphoteric substances, meaning that they can act as both acids and bases. For example, the first reaction shows beryllium hydroxide acting as a base, neutralizing sulfuric acid. The second reaction shows beryllium hydroxide acting as an acid to form the complex ion berylate. In several ways, beryllium behaves more like aluminium than the other group 2 elements. It's worth being familiar with the details of this diagonal relationship. First, the beryllium ion and aluminium ion have similar charge to radius ratios as shown here. Neither beryllium nor aluminium reacts readily with acids due to the oxide film that both the metals exhibit on their surface. The hydroxides of both the metals dissolve in solutions of excess hydroxide to form complex ions. In the vapor phase, both beryllium chloride and aluminium chloride form chloride-bridged structures. Both the chlorides are soluble in organic solvents, reflecting their essentially covalent character. Both the chlorides are strong Lewis acids, acting as electron pair acceptors in chemical reactions, as shown in the reaction given here. Both the chlorides are used as catalyst in the Friedel-Crafts reaction shown here. Both beryllium ions and aluminium ions form complex ions. Next, we will consider some important compounds of calcium. Calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate, and cement. Calcium oxide, which has the chemical formula CaO, is commonly known as quicklime. Calcium oxide is a white, amorphous solid with a melting point of 2870 Kelvin. To prepare calcium oxide on an industrial scale, limestone or CaCO3 is heated in a rotary kiln at 1070 to 1270 Kelvin. At these conditions, calcium carbonate decomposes to form calcium oxide and carbon dioxide. The carbon dioxide is removed continuously to drive the equilibrium to the products. Quicklime absorbs carbon dioxide and moisture from the air, as shown in these reactions. When carbon dioxide is absorbed, calcium carbonate is the product. Slaking of lime, shown in the second reaction, refers to the process in which, when a limited amount of water is added to a lump of lime, it breaks up and results in the formation of a suspension of slaked lime along with the liberation of heat. This reaction also shows that calcium oxide is a basic anhydride, since its reaction with water forms calcium hydroxide, which is alkaline. Calcium oxide is a basic oxide and thus can combine with acidic oxides at high temperature. For example, reactions with silicon dioxide and phosphorus pentoxide are given here. Calcium oxide has a number of industrial uses. It is necessary for the manufacture of cement and is the cheapest form of alkali. It is used to produce sodium carbonate from sodium hydroxide, also known as caustic soda. It is used in the purification of sugar and in the manufacture of various dyes. Calcium hydroxide, another important compound of calcium, is commonly known as slaked lime. It is a white, amorphous powder that can be prepared by adding water to calcium oxide. Calcium hydroxide is only sparingly soluble in water. Aqueous solutions of calcium hydroxide is commonly called lime water. Milk of lime is the common name for suspension of calcium hydroxide in water. Lime water provides a simple test for the presence of carbon dioxide. Lime water turns milky when carbon dioxide is passed into it. A precipitate of calcium carbonate forms in this reaction, as shown here. If more carbon dioxide is passed into the above solution, the precipitate dissolves and forms calcium hydrogen carbonate. Milk of lime, a suspension of calcium hydroxide in water, reacts with chlorine gas to form calcium hypochlorite, the main component of bleaching powder. Hypochlorite ion is a good oxidizing agent. Calcium hydroxide is an important industrial chemical. It is used in the preparation of mortar and to make whitewash. It is necessary for making glass as well as for the tanning of leather. As was just discussed, it is used in the preparation of bleaching powder. It is also used in the purification of sugar. Calcium carbonate occurs naturally in several forms, including limestone, chalk, and marble. In its pure state, it is a white, fluffy powder that is nearly insoluble in water. Upon heating, it decomposes to form calcium oxide and carbon dioxide. Calcium carbonate can be formed in two ways. The first process involves passing carbon dioxide through slaked lime, as shown here. Alternatively, sodium carbonate reacts with calcium chloride to form calcium carbonate and sodium chloride. This is shown here. Calcium carbonate is used for a variety of purposes. It is well known as a building material. It is necessary in the manufacture of quicklime. It is used industrially as a flux in extracting metals from ores and in the manufacture of high-quality paper. It is also used as an antacid. Calcium carbonate is an ingredient in toothpaste and chewing gum and is used as a filler in cosmetics. Plaster of Paris is a hemihydrate of calcium sulfate. Plaster of Paris is formed when gypsum or calcium sulfate dihydrate is heated to 393 Kelvin. The decomposition reaction is shown here. If gypsum is heated above 393 Kelvin, anhydrous calcium sulfate or dead burnt plaster will be the product. When water is added to plaster of Paris, it forms a plastic, malleable mass that hardens in 5 to 15 minutes. Plaster of Paris is used in the building industry. In medicine, it is also used to prepare casts to set bone fractures. It has applications in dentistry too. Besides, plaster of Paris is used for ornamental work, such as the ceiling medallion shown here, as well as statues. Cement, or Portland cement as it is often called, is another important compound of calcium. The raw materials for making cement are limestone and clay. The composition of cement is not fixed. Portland cement typically contains 50 to 60% of calcium oxide and 20 to 25% silicon dioxide as its main components. Cement also contains 5 to 10% aluminium oxide, 2 to 3% magnesium oxide, 1 to 2% iron 3 oxide, and 1 to 2% sulfur trioxide. In good quality cement, the ratio of silica or silicon dioxide to alumina or aluminium oxide is between 2.5 and 4. The ratio of lime or calcium oxide to the total oxides of silicon, aluminium and iron should be as close to 2 as possible. Cement clinker is formed when clay and lime are strongly heated. They fuse together to form cement clinker, shown in the photograph. To form cement, 2 to 3% gypsum by mass is added to the cement clinker. This mixture is then ground to make cement. Ingredients that make up the bulk of Portland cement include dicalcium silicate, making up 26%, tricalcium silicate, contributing 51%, and tricalcium aluminate, contributing 11%. Cement sets when it is mixed with water to form a hard mass. The molecules of the components get rearranged and hydrated. The presence of gypsum slows down the setting process so that it gets very hard. Cement is used to make concrete and reinforced concrete. It is used in plastering as well. It is best known for its use in the construction of bridges, dams, and buildings of all sorts. Both magnesium and calcium play important roles in biological systems. An adult human body contains 25 grams of magnesium and 1,200 grams of calcium. Compare this with only 5 grams of iron and 0.06 gram of copper. Let's go into these important functions in more detail. Phosphoryl transfer enzymes, which use ATP in phosphate transfer, use a magnesium ion as a cofactor for enzyme function. An illustration of one such enzyme is shown here, with the magnesium ion shown in green. Chlorophyll is the main pigment in plants that absorbs light for photosynthesis. The porphyrin ring in chlorophyll contains magnesium. Bones and teeth contain about 99% of the calcium in the human body. Bone, which is alive, with a complex structure, is continuously being solubilized and redeposited in the body. Approximately 100 milligrams of calcium are dissolved in 1 liter of plasma. This concentration is regulated by the action of 2 hormones, calcitonin and parathyroid hormone. Calcium ions play an essential role in muscle contraction. A diagram of the sliding filament theory of muscle contraction is shown here. Calcium ions also play an important role in blood coagulation. Calcium ions are essential for the transmission of signals between nerve cells. Calcium ions are important for cell signaling and for various physiological processes. Calcium channels regulate the transportation of calcium ions across cell membranes.